Good morning, sir. Good afternoon, sir.
Very good afternoon. So I'll start this course after waiting within 2 minutes for that if anybody else is joining. So in that time, let me finish the introduction. So myself is Subhajit Kundu, uh, PM TA for this course. So in this live session, we will mainly discuss the problems for that particular week. So today is the very first week of this live session. So continue next 12 week with additional one extra week, that is week 13. I will discuss the problems of the content which has been taught in that week. So these problems will be very different from, not very different from that problems which can be asked in the final exam or in the assignment which is uploaded in the portal. So basically this problem is a different problem from the portal assignment. Also, if you have any doubt regarding that particular week, you can ask me, or any other doubt regarding this chemistry. So this transition metal organometallic chemistry principles to application in this course is the starting of the series of a course. That is, there is two course in this, another two course is there. So this is a principle to application is the starting course, and this will followed by the next semester, that is in the spring semester, advanced transition metal organometallic chemistry. So where we will discuss mainly the application of the transition metal complexes. So basically first, for in this course, that is principle to application, we will discuss the different types of ligands which form the organometallic compounds and how they are bonding and their reactions. And the next course, that is the advanced transition metal, in next semester we will discuss their application. So in that way, this is a two consecutive course in that 1 year. So if you feel, you can take the course in the upcoming spring semester also. So I think 3 people are joined. So if you have any doubt regarding this week, you can directly ask me. So I will start with the doubt. If not, then I will show some sample questions which I have made or from the previous year's assignments or the exam questions. So you can ask them. After that, at the end, when I will share 10 questions, so after that I will discuss the content in a very brief or summary of this week, so that you get an overall idea of this week. So again, and another thing, during the portal thing, which I will also show, that in the portal there is a option to ask question directly from the portal assignments or exam pattern, or any doubt which is in that, you can ask in the portal question. There is an option Q&A tab, so there you can post your questions. So we will try to answer those questions from with discussing with the course instructor as soon as possible. And after that, the questions which I will discuss, if you have any doubt in that questions, you can directly email me. I will share that email address to get your doubt cleared. So don't mix those things. So if you have any doubt in the portal question, just upload in the portal or you can ask me. But for my questions which I will share, you can only directly ask me through mail or to in the live session in every Sunday, that is from 4 to 6 in upcoming 12 weeks. So next 12 Sundays we will discuss that every week content through the question answer, and also I'll summarize the course content after discussing the mainly the reason for this session is to interact with the student who has already taken the course and share your thoughts or doubts in this course and get your doubt cleared. I will try to improve the content as long the course go on in forward direction. Also, I will try to increase the number of questions in every Sunday so that you can be more competitive or more tricky question which will be helpful for you to solve in the final exam. So first I will show how to ask question in the portal or the portal assignment or any doubt directly to the course instructor. Then I will start this session. Uh, okay, now I think the screen is visible. So this is the portal which you will see when you enroll this course. So here is the tab Q&A. So if you click on it, it will go to a window or a Google discussion forum. So you have to just post your doubt in this discussion forum, and we will discuss with the course instructor professor, and then we will post this doubt, the answer, and you will get that. So also you can ask their doubt in the this live session. So if you have any doubt from my session, it is very clear. So I request you, please don't post that in the Q&A. You directly ask me, that will be better for me, because the professor. Okay, so this is the discussion forum. You can ask by clicking with a new conversation. When you click on the new conversation, it will open up a dialog box, new conversation in discussion forum for transition metal organometallic chemistry. So you just click the subject and post messages. So we will reply to your messages as soon as possible, and you will get your doubt clear. So this is the best way to communicate in this course whoever has registered. So then okay. So let's start this session by sharing some sample questions. So this is the just beginning. So we will discuss the history of organometallic compound and some basic questions or example of organometallic compound, and then we will discuss some important topics which has been taught and the question which fundamental question which can be asked during the examination. So here the email address, my email address is shared here. So again I am introducing myself. My name is Subhajit Kundu, and you can send me email in this email address for your doubts or my question, which I will show in every next 12 week for your understanding and for this course. Okay, so let's start just today's first question. So no, nothing very tricky or very discussable question is there in today's session, as we are just started the course. So as we will move on or go forward in this course, you will have to see some questions, and after ending of this session I will share the recorded video of this discussion or whatever has been discussed to the recording sheet. You can follow that. Also the questions which I have discussed will be uploaded in that sheet, so you can go to the directly that Google Drive to get those questions. Remember that the answers will not be there when I upload this PPT or presentation. So for the answer you have to go to the recorded video for that week and the explanation. Okay, so today's first question is: the first sandwich complex ever synthesized was? If you know the answer, you can directly answer me, or then I will answer.
Sir, is it kerosene?
Yeah. So first synthesized complex is ferrocene. Ferrocene, the Cp2Fe, is a fast synthesized organometallic complex. So can you tell me the overall valence electron count for this complex?
Any electrons?
Yes. So ferrocene have 18 electron. So we will discuss the 18 electron rule at the end of this session. So here the iron have, so we will do it in neutral method. So iron have that how many electrons? 8. And ferrocene
8.
and Cp ring, that is the cyclopentadienyl ring, will share the 5 electron. So we have 2 cyclopentadienyl ring, so 5 into 2 will be 10, and iron has 8 electrons, so that will be 18 electron system Cp2Fe. The next question is: the recorded account of first organometallic compound ever made it. This is also same question but different.
Sir, is it ceases salt?
No, the first ever compound, first ever organometallic compound. The recorded account of first organometallic compound ever made is this first ever compound.
Option 3, sir.
Yes. So first is the crocodile.
Crocodile oxide.
So here you can see that 2 question is there which also asks for the same type of question. The previous question was also asked the question, that is the first synthesized complex, but here is a sandwich complex. It is mentioned. Whereas in this question, it is said that the recorded account of first organometallic complex ever made. So it is a crocodile oxide. What is the formula of it?
CH3 twice. AX.
Then can you repeat?
Dimethyl acyl oxide.
Yes, 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 yes. So this is an oxide of arsenic, right?
Yes, sir. Right.
Yes. So here the option number 3 will be right answer. The next
Okay, sir.
is the valence, the 18 valence electron rule is obeyed by. So option A, the class 1 and class 3 complexes, class 1 and class 2 complexes. Option 3 is class 1, 2 and class 3 complexes, and option 4 is class 3 complexes only. Now tell me what will be the answer. So this is the mark. The 18 valence electron, that is 18 valence electron rule is obeyed by. So according to the 18 valence electron rule, complexes are classified, that is the total valence electron. After counting the total valence electron rule, the complexes are classified into the three categories: the class 1 complexes, class 2 complexes, and class 3 complexes. There is very minor difference in these three categories, but we have to remember it this. So what will be the answer? Okay, I know it is difficult to say the answer because the idea of this class 1, 2, 3 is not that very clear. Okay. So for the class 1 complexes, let me clear it. So class 1 complexes have the valence electron which is not 18 but any value. Okay, so remember that for the class 1 metal complexes, the valence electron count is not 18 but it can be any value, that is from 12 to 22 it can be any value. So we call this a class 1 complexes. Okay, for the class 2 complexes, we said that it can be any value, valence electron can be any number, but it should be less than 18. And the class 3 complexes which are only obey the 18 electron rule. So that three classes are there: class 1, class 2 and class 3. So class 1,
Option 4.
option
4.
it says that the 18 electron rule is obeyed by. So let me tell you again that the class 1 complexes which the valence electron can be any number. Okay, that means, but it is not 18. Okay, that means it can be 12, 13, 14, 15, 16, 17 but not 18. It can have the number 19, 20, 21 and 22. For the class 2 complexes, any number but it should be below 18. Okay, that is, it will stop at 17, not 18. And for the 18 valence electron complexes, we have only made the class which is class 3 complexes. So here the question says that the 18 valence electron, that is 18 rule, is obeyed by. So 18 valence electron is rule is specially made for the class 3 complexes only. It is
Class 3.
exclusively for the class 3 complexes. Whereas any number of valence electron except 18, we called it class 1. Any number of electrons, valence electron, which is if it is less than 18, we call it class 2, and for the 18 electron we call it class 3. So generally the value which is numbered below than 18, we can call it as a class 1 or class 2, can be both. Okay, so that's why the question is the 18 valence electron rule, that is specially designed for the class 3 complex. So here that option 4 will be right answer. Next, that is the Ziegler and Natta catalyst is used for. Option A is the olefin hydrogenation reaction. Option 2 is Mond process. Option 3 is epoxidation, and option 4 is the synthesis of stereoselective polymers. The red tick you can ignore because it is
Option 4.
yes. So Ziegler and what is the catalyst used for Ziegler and Natta? What is the chemical composition of this catalyst? So here option 4 is the right answer. Now tell me the chemical composition of this catalyst.
This is titanium complex, right?
Triethyl aluminum and titanium chloride.
Yes. So it is triethyl aluminum and the TiCl4 is a combination which gives these complexes. Okay. The next question is, so here option hmm. 4 is the correct answer. Then option 5 says the maximum number of valence electron that a class 1 type complex can accommodate is
22.
yes. How it become 22?
So because class 1 you mentioned that it cannot accommodate 18 electrons, but it can obey any electrons between 12 to 22, except
Yes.
18.
Okay. So now why it stopped as 22, not after that? That is the question. In the option there is all number higher than 22. So minimum, so if the option is let's say 16, 19, 21 and 22, then what will be your answer? So if the reason should know why it stopped as 22. Any idea?
No, sir.
Okay. So we are considering the d electron system, right? The d metal orbitals. So d metal, that is the d have the 5 orbitals. Okay. So 5 orbital can accommodate maximum of 10 electron. Then we have the p electron and that s electron. So p have that 6 orbital and the s has 2. So that is the total we are getting in a shell is an 18 electron. Now that extra 4 electron, which is can be that antibonding site of this d orbital, that is the we will see the metal or orbital in the next lecture, that is the MO diagram. When the d orbital splitted, that we have know that d orbital had T2g and Eg level. So each when T2g Eg level and p and the s orbital, so all these orbital filled, we will have that total electron, that is the 5d orbital filled, that is the T2g and Eg. Okay, which will give the 10 electron. Then we have the p orbital into contribution, which will give the 6 electron, and then we have the s electron, which will give the 2. So 10 plus 6 plus 2, then it will be 18 electron. Now if the ligand system contribute the more electron, so it will be housed or it will go to the in the antibonding orbital. So now for this system, the antibonding orbital will be Eg star. So Eg star has the also 2 orbital, so that can occupy maximum of 2 electron. 4 electron. 2 orbital can occupy maximum of 4 electron. That is 8, another 4 electrons. So 8 plus 4 is 22. The other antibonding orbital, if you say the p star or sigma star s, so that is the energy is so high that it cannot be occupied in either normal condition or any condition. The molecule cannot be stable. So that's why the maximum number of electron which can be occupied is the 22. That is, it is from the 5 contribution from the T2g Eg, that is the 5d electron, which have give the 10 electrons. 5d orbital will give 10 electron. Then contribution from the p, that is total 3 orbital, give the 6 electron. 2 from the s, that is another 2 electron, that is 18, and another, if ligand contribute more electron to the metal, then only then it will go to the antibonding orbital of the system, that is the Eg star. So there it will be another 4 electron. The other antibonding orbital, let's say if s is there, so there will be another antibonding orbital, s bonding, so another antibonding will be s star, that is the sigma s star, and p is there, so there will be p star also. But this orbital energy is so high that under normal condition it cannot be occupied. Only up to the Eg star can be occupied. And if you say the T2g orbital, so T2g orbital will be specially non-bonding, so there will be no antibonding orbital for this. So there is, so if you get the molecular orbital, so the maximum number of electron can be 22 in normal condition. Okay, not more than that we can be occupied in normal condition. So maximum number of valence electron of any type of complexes cannot be more than 22. So when the next class I will show that molecular orbital diagram, then I will explain this system in more detail. Is it clear?
Yes, sir.
Okay. So 5 plus 3 plus 1. Okay, 5 plus 3 plus 1, total 9 orbital. P, D, P and S give the 18 electron, and then extra 4 electron coming from the anti-bonded orbital of the D orbital, that is the Eg star. Okay, so next class we will discuss it in more detail. The next question is the valence electron count for palladium in palladium Cl4 2 minus is. What will be the valence electron count? Palladium in which group?
So nickel.
Yes. So what is the valence electron count for palladium chloride 2 minus? Do it in neutral method and tell me what will be for the palladium, what will be for the chloride, and what will be for the 2 minus. What will be then the total electron?
So it is 16.
Yes. Now tell me how it becomes 16. Explain.
So yes, palladium actually follows is a nickel group. So nickel configuration is D8S2.
Yes. Then.
Yes, sir. So 8 plus 2, 10 electrons. So chlorine has, so there are 4 chlorine atoms. So chlorine can donate 1 electron. So 4 into 1, 4 electrons. So plus 2 electrons, 2 minus is there. So 2 electrons extra. So therefore, like for 4 plus 2 plus 10 becomes 16.
Yes. So you are doing it in the neutral method, right?
Yes, sir.
So how it will be in that if you do it in the ionic method? Okay, neutral method is more convenient, so you can do it preferably in the neutral method. Okay, so here the 16 electron valence will be the right answer for these questions. The next is the number of electrons that the Cp ligand donates in its neutral form and negative form is. So that's why in the last question I asked, do it in the negative means an ionic method also. So you have to know both the mechanism. You may do it always in the neutral method, but you should have an idea also of the ionic mode.
So is it option 3?
Yes. How?
So because in the neutral form, like cyclopentadiene shows like 5 electrons. And then when it comes to negative form, what happens is since minus charge is there, so one more electron gets added. So 5 plus 1 becomes 6.
Yes. So for the Cp ring or cyclopentadienyl ring, it will in the neutral method it will donate the 5 electron. So we will consider the 5. But when we go to the ionic method, for the any cyclopentadienyl complexes, if we do the calculation in ionic method, we have to calculate it as a 6 electron system, right? The next question is
Yes, sir.
the number of d electrons and the number of valence electrons in iron oxalate complex respectively. So C2O4 is which acid anion?
Oxalate ion.
Yes,
Ion.
oxalate anion. So oxalate anion is 2 negative charge.
Minus 2.
Yes. So now calculate the valence electron. It should be oxalate 3.
Yes, I'm getting around minus 1.
So
should be 3 plus 3.
Oxalate 3. Calculate it as oxalate 3 oxalate ion would be there. Okay. Now it's correct.
Sir, what? Like you are saying FeC2O4 3 and 3 minus, right?
Yes.
Okay, sir. Yeah, that is right. Siren is coming plus 3 oxidation state.
Yeah. Yes.
So it is D5, sir.
And
That
the
is 5 electrons.
number of d electrons and the number of valence electron. So total valence electron is
Total valence electrons for iron is 8. Total valence electrons for iron is 8.
no. The total valence electron in the complex.
Oh, yes, sir, complex.
So you see the read the question. The number of d electron and the number of valence electron in this complex respectively.
Yes, sir. So is it 17 electrons?
Now tell me how it becomes 17 like the previous one.
Yes, sir. So because just mentioned FeC2O4 3 minus. So iron has totally 8 electrons, and then oxalate can donate 2 electrons. So 3 into 2 becomes 6. Plus 3 minus is there. That is also counted. So 8 plus 6 plus 3 becomes 17.
Yes. So option number
Option number 2.
yeah. Option number 2 will be the right answer. So option 2 5 and 17 will be the right answer for this question. The next question is the compound Fe2CO9 has 1 Fe bond, 2 Fe bond, 3 bridging CO, 4 bridging CO. So for this type of question is very difficult to predict if you don't know the structure. So some common structure like Fe2CO9 or another is there Fe3CO12, some osmium complex like osmium 3CO12. So some questions are there, some structures are there which is very common and it is asked in every examination. So without the structure I think it is not able to possible to tell how many this CO bridging is there, because there is no other way to predict this.
So we can use that metal bond formula.
Metal bond you can calculate by if the compound obey the 8 electron rule only, right?
Yes, sir.
Otherwise you cannot do it. So here
Yes,
that this compound obey the 8 electron rule and the metal bond will be
1.
So one metal bond will be there. So one iron bond will be formed. And what will be the number of bridging CO?
Sir, that I am unaware about it.
Because the structure you have to know. So some structure, please remember when you are going through this course, some of the structure which is important. So that is also my duty to note which structures are important. So Fe2CO9 is a very common structure in the metal carbonyl segment of organometallic compound, which have to remember. So not only in this exam, in other exam also ask these types of question. Another PS this they also ask Fe3 CO12. It is a higher analogous of iron. So here in this structure, one iron center and another side another iron center is there. This pen is not working. So and each of the iron have three terminal CO. 1, 2, 3. Okay, so 6 CO is
Yes.
gone and rest of the 3 CO is the bridging CO.
Okay, sir.
Okay, so the structure is somehow like this. So when it is iron 3, so Fe3CO12, there is how many Fe bond will be there? If it is Fe3CO12, it also will be the 18 electron rule.
2 bonds.
3
Two
Fe
two
bond,
metal bonds.
3 Fe,
Ah, sir.
3 iron will be there.
Yes, sir.
So that will be form
Yes,
a
sir.
triangle.
Triangle structure.
3 Fe bond will be there. So here interesting thing is that number of bridging CO. So one of the iron will be not performing bridging and other two will perform in the bridging. Look for the structure when you read this content in the upcoming slides. Okay, and
Yes,
also
sir.
the structure of osmium compound OH3CO12. So now only thing you can remember that when you are going down the group, right, iron, ruthenium, osmium, that size become very increases, size become
Atomic size
varying.
increases.
So that's why when you are going down the group, that is from iron to ruthenium to osmium, the formation of the bridging compound, like the bridging carbonyl, become very less. So for the osmium complexes, generally you will see all the COs are non-bridging and it exists as a terminal
Terminal form.
CO. But for the iron and ruthenium, some complexes are known which are acting as a both bridging and terminal. Now tell me how you, if you have two complexes, one complex has one, if you have one complexes which have both bridging CO and terminal CO, and you have another complexes, it may be any complexes which don't have any bridging CO. Now tell me how you can simply identify it by do a simple measurement or with the help of simple instrument. What
Like
instrument?
you can check using IR spectra, right? Like IR spectra.
How you will distinguish?
Like you have to find out the CO stretching frequency
Huh.
and bending frequency.
Then what will be the difference?
Like sir, what I can say is like if the stretching frequency increases, means what happens is like it will show the presence of a peak that indicates that it's a bridging ligand.
No. Increases, you will measure it. Let's say you have these iron complexes Fe2CO9, you measure it the IR, and if you have another complex, let's say osmium OH3CO12 have complex, you measure the IR. There is no increase. You will see two different spectrum, right? So now by seeing the two different spectrum, how you will say that this compound has both kind of CO and another compound has or another complex has only one type of CO. Very simple.
The difference is like in the case of iron, what happens is bridging is there, but for osmium we don't have bridging. Everything is terminal.
But how you predict by looking at the IR? What differentiator will be? That means that the carbonyl stretching frequency you will observe, and for the iron case you will see the two types of carbonyl peak,
Yes, sir.
right?
Like stretching and bending. You
No,
mean?
no, no, not stretching and bending. Both are stretching. Bending is will be in the fingerprint region. You cannot detect.
Okay, sir.
Okay. So here for the iron case or any complexes having two different types of stretching. For the bridging one, as the carbon donated is to the both the metal center. Okay, so that will have the different stretching frequency compared to that carbonyl group which is attached terminally. Okay,
Yes,
so
sir.
to two different peak, different carbonyl peak you will observe. As there is no other organic moiety, so if you run the IR spectra for two complexes where one only terminal and one both terminal and bridging is there, so you will have the two spectra where you will see two different distinguished peak, and another spectra where there is no bridging you will have only one peak, because all the carbonyl groups are
Terminal.
equivalent.
Yes, sir.
Okay, that's why it will say two peaks. So by
Yes,
looking,
sir.
by running the IR you can say, but it also depends the symmetry of the complexes. It as you will go move further, we will see that when the symmetry breaks down for a complexes, the number of stretching frequency also increases. Okay,
Yes,
so
sir.
for three bridging here, for these complexes, as I draw the structure, you can see that three bridgings are equivalent. There is no difference between the three carbonyl group which makes a bridge. So if there it arrange some orientation, there two are like one kind and another carbonyl is another kind, or another effect is there. So for the bridging also you will get two peaks. Okay, so that depends on the symmetry and the equivalence of carbonyl group. So here, so three bridging C will be there, and there will be one iron-iron bond. So this question is a MSQ type question. So MSQ type question is also part of your examination. So when you are reading or you are practicing question, try to remember that it can be MCQ, it can be MSQ questions. Okay.
Yes, sir.
So here option 1 and option 3 will be the right answer. So here it is a
Actually, one more thing, one more doubt I have. That is, you mentioned about iron complex and osmium complex. So, which means for an iron complex, we get two peaks, one for terminal, one for bridging,
yeah.
CO. But for osmium, we get only one peak for terminal. That's all.
Yes, because there is no bridging.
Yes, sir. Right.
Okay.
Yes, sir.
Also, when we discuss the nickel carbonyls or any metal carbonyls, when we remove, let's say nickel carbonyl, we have four carbonyl group. So we put one carbonyl group and put another ligand. So that will be NiCO4 1L. Okay.
Yes,
So
sir.
when we put another carbonyl group, remove another carbonyl group and put another ligand, that will be NiCO2L2. So when this symmetry is breaking, like from the tetrahedral to C3b or in another lower symmetry C2b, so then if you present the two carbonyl group, the two can be also different. So the
Yes, sir.
spectra which we see always, any kind of spectra, for IR spectra or like NMR, you may know more about NMR. So when the symmetry breaks or equivalence breaks, the number of peaks increases, right? In the NMR also, if we
Yes, sir.
see know that if the two proton is not equivalent, there will be appear in distinct peak in NMR spectra. Here also same, if the two carbonyl groups are not equivalent, it will give two separate peak.
Yes, sir.
Okay.
Yes, sir.
The complexes here that follows the 8 electron rule is or are.
Like as you mentioned earlier, it can be like an MCQ or MSQ, right?
Yes. The question will be both. In final exam, in the total assignment question, we also have MSQ and MCQ mix up. So when you
Yes, sir.
answer, please be very careful that question is MSQ or MCQ. complexes that follow the 18 electron rule is or are. So for the 4 complexes you just need to calculate the valence electron count, which is very simple. Now calculate every complex the valence electron and tell me what will be for all the complexes 1, 2, 3, 4.
Yes, sir. So is it option 2 and 4?
Yeah. Tell me the valence electron for each. Like for the copper, how we calculated, and for the copper, how many electron copper is there?
Copper is D9S2,
D9
11
is 10.
electrons.
So how many electron for the copper you calculate? So
11
first will be
electrons.
9 plus 2,
Yes, sir. 11.
11. Then for another 6. So
Yes,
11
sir.
plus 6 will be
17.
17 plus 2, right?
Yes, sir. 19.
That will be 19 electron. And then for the iron, tell me.
Iron, like 8 electrons plus 5 into 2 electrons from carbonate
That will
becomes
be
10. So 10 plus 8, 18.
So one option is 2 option correct.
Yes,
Then
sir.
option 3,
K, PTC,
platinum.
L3. Yes, sir. So platinum is actually nickel complex. So 10 electrons plus 3
10.
electrons plus 2 electrons.
10 plus 3 plus 2.
Yes, sir.
That is also,
15
and minus, there will be one minus.
plus 1, 16 electrons.
Yes, that will be 16 electron.
Yes, sir.
And for the platinum, last one.
So platinum contains 8 electrons. Fluorine has 1 extra electron. So 8 plus 6,
14.
14. Yes, sir.
Then
Then 2 minus is there, right?
yes.
Yes, sir. That is also coming 16. Sir.
Yes.
Okay, sir.
That means platinum is an 8 electron. 8 plus 6 is 14 plus 2 is 16. So only option 2 is the correct answer.
2 is the correct.
Okay.
Okay, sir.
So this gives that end of this today's discussion to the question. Now if you have any doubt regarding these questions or any doubt from this topic which has been taught in this week, you can ask me.
Sir, actually, I have not gone completely through the things, so I just gone halfway through the videos. So the only thing is, currently you're just talking about that periodic metals, right? Like whatever elements are available in the periodic table, that only you're talking.
Yes, I did not get it. Can you repeat?
I repeat, sir. So what I want to say is, like, week 1 lectures are uploaded. So I haven't gone through all the lectures. Only some lectures I've gone through. So you are actually starting only with the elements itself, right? Elements present in periodic table. That is the D block elements. Okay, sir. Now, next, when you will be like teaching about those all coordination complexes, like total valence electrons and skeletal electron pair.
Yes.
Will those will be upcoming?
Yes, that will be upcoming. So let me give you a brief overview. So this course, as I starting in the says that this course is the starting of organometallic chemistry. So this course first you will see that some different types of ligand system. Let's say we talked about cyclopentadienyl ligand system today. So ligand system start not from the carbon number 5. It starts from carbon number 2, that is the ethylene also see in the gaseous salt. So now from the 2 number of carbon, 3 number of carbon, that is the cyclopropene ring, 4 cyclobutane ring, 5 cyclopentane ring, 6, Erin ring 7 and 8. So these will go on, and after that we
Yes,
will also discuss some metal carbonyls, metal nitrosyl complexes. So this is going to be a very long series. So this is just a starting. That's why in today's content I will only put some questions which has already been taught in your BSc. That is, you are in BSc or in MSc? I have no idea.
no, sir. Actually, I have completed my masters.
Oh, then it will be very easy for you. Okay, okay.
Yes, sir.
So
Yes,
then
sir.
why you are taking this course?
No, sir, because I want to like pursue research in this organometallic chemistry. So that's why I want to like be thorough with the basics of organometallic chemistry. So which will help me in this PhD.
Okay, okay. So have you qualified NET or GATE?
Not yet, sir. Like this next year, I'll be giving the exam.
Oh, okay. So you are preparing for NET and GATE to clear to enter in the PhD admission, right?
Yes, sir.
When you completed your masters?
Last year itself, September 2024.
24. No, that's long year ahead. Like you have many times to think and do PhD. Okay, so you can do PhD without NET also. Just qualify at the gate and you can enter that top IITs by giving a good gate score also. You know it?
Yes, sir. Like by clearing the gate itself, we can like cut off itself. We can go inside any IITs, like top IITs.
Yes, sir. Top IITs. Like I am from IIT Bombay. I am doing research in IIT Bombay. So in my third year of
Oh.
PhD. So you can also join in top IITs like IIT Bombay, Madras, and Delhi.
Yes, sir. I want to go to IIT Bombay, Madras, and Delhi, sir. I
So
want
you
to
are
like,
you are
secure
from
admission.
which state?
Chennai, sir.
Okay. Then it will be easy for you. So each year, if you are not, I don't know, not sure, well, they also declare some good amount of vacancy for that category for the gate. It is called TA, teaching assignment assistant category. So there, if you qualified your gate examination with a good score, you will get the interview call. I think criteria is to get a good score within 500, a good rank, get rank within 500.
For rank within 500. Okay, sir.
So I think
Then I have to get very good marks in gate exam.
then
Like not below the cutoff, but
if
just
you
very good
have rank
marks.
within 500, then you will get
Yes,
the
sir.
interview call, and then you can uh, get into the PhD admission. Okay, so NET
Okay, sir.
JRF is not the only criteria, but if you have qualified JRF, that your choice to choose a supervisor or choose a professor with your interest will be better, will be
Okay,
more
sir.
greater, not better, it will be greater. Like you can join any institute, whether they are providing you the uh, fellowship or not. You have your own fellowship. That is the point of clearing NET JRF. Otherwise,
Yes, sir.
some small institute, or not small, but I will say that better say that they no don't have vacancies with grade. Okay, so like if you join like ISC Bangalore or some NITs or some new IITs, they have very less vacancy of for the GATE candidate, and that vacancy is also specified to few professors. Like if you join as a GATE student, you have to choose that professor only, not every professor you can choose. Okay, so that
Yes,
is
sir.
the, I can say that is the drawback of qualifying GATE, and not drawback of GATE, but admission taking into institute with a GATE. So focus on
Yes, sir.
CSR NET only, and to get your own fellowship. So you will have your choice when to whoever you can join you according to your choice.
Okay, sir.
Okay.
Okay, sir. Like you are asking me to like look for net also, like not gate
Uh,
alone, but
no,
both gate and
I'm
net. So,
asking for focus on the NET exam only. GATE exam, now, right now the ONGC and other thing is also not that much regular. Okay,
okay, sir.
so either you focus on, if you want to pursue PhD, so it is very much you should focus on the NET exam to get a clear the GRF. Now GRF is also not very easy to clear, because every
Yes.
year I have seen it that from my 2020 to 25, this 22 plus 3 4 year cutoff has been increased in by, like, let's say 10 15 marks. So that is not easy. That's why if focus on the GRF. If you want to get a job, focus on the other exam, but if you want to pursue PhD, you have to get the GRF.
Okay, sir.
If you have, do you have any other question related this course, or any question related to chemistry, you can ask me.
No, sir. Only thing is, I just have to go through all the lectures which has been uploaded.
Yes, you can. If I suggest, if you can go through all the lectures, that is good. And also there is a transcript, that is that book type thing, which is also available in the portal, I think. That you can also read if you don't have like time to, and that is exactly the same thing which has been talked in or speak in the lectures. You understand what I am saying? You may not understand. Let me show you. There is a, like, whatever the professor says in the video lecture, there is a book. You can download it from that portal website. Okay, so you can also read it if you don't want to go to the lectures. That is exactly same whatever in that taught in the lectures. So you will get like 3 4 lectures within 1 hour. So you are
Okay,
going to
sir.
give the exam or not for this course?
Like this year, you are saying?
Huh?
Yes, sir. I will be giving the exam for this course. Yes, sir. I will be giving the exam.
Yeah. So here it is a book. You can get it from that website portal. There is a downside, you can see. So downside you will see it. So let's open and I will show you. So with this book you can just read it, and here slides is also there, I think. A picture of the slide. So you will get it quickly. You will understand that what has been taught in this week. Or you can also follow through
Yes,
the
sir. So
video.
actually, are you sharing the screen?
No, I am not share started because the book is not opening. I will share.
Okay,
I
sir.
can share it also in the drive. You will get a list from the recording sheet list. Huh. After this,
Yes, sir.
after
Sure.
this, you will get a drive link there, and then YouTube video link for today's discussion. So here there also you can get that book. I will also upload there.
Okay, sir.
Okay. So if not, then you can leave or you can stay, because I have another 30 or 35 minutes. I have to discuss some of that summary of this course, summary of this week, first week content, which is more important.
Okay, sir. You may discuss.
Okay. Screen. Yes, this one is available in the portal. You can go through it.
Yes, sir.
In the portal, in the last option, like live left side, you can see it, and you can check it. Huh. So here whatever is being said, that is, you can say that is that like subtitle of that video has been recorded, right? Okay.
Yes, sir.
So you can also go through it, so which will help you to cover the lecture faster. Okay. And here the
Yes, sir.
slide is also there. let's say this is the first organometallic complexes which has been synthesized fast, which we already talked. This is the cacodyl oxide. Then another important, how many lecture you have covered? First 3 lecture.
Yes, sir.
Okay, so I suggest you to go through this, so you will cover faster, and then if you anything remains after this, if you cannot solve after reading this, then you can go to the video for better understanding. Also you
Okay,
can
sir.
join from the next Sunday to every Sunday, like the upcoming 12th Sunday. So I will discuss more questions, and we will have a regular discussion regarding this course. I'll be happy if you get some questions and we will discuss in the video in this
Okay, sir.
series.
Okay, sir. Sure.
So here one question is there. I can ask that when the CP ring is bound to iron, it is highly stable complex, that is the ferrocene. But when the
Yes,
2CP
sir.
ring is bound to beryllium Be, it is highly unstable. Explain why. I think this is covered in these first 3 lectures, right?
Okay,
In
sir.
polarity,
Yes, sir.
you have must read it. That first, can you explain?
Okay, sir. Like what you're saying is like for ferrocene complex CP ring is stable, but when it
No, no,
comes
no.
when
The ferrocene complex, not CP ring. For the complex, ferrocene complex, when the CP ring is bound to iron, it is highly stable. But when it is bound to beryllium, it is not that very stable. Complex is not stable.
like instead of ferrocene, if beryllium is placed, then it is not stable. You were saying.
Yes.
Okay, sir. So because like I can say like beryllium actually falls in the S block.
Huh. Yes, this
So
one.
like
You can see my screen, right?
yes, sir.
Extremely, you can see that beryllium complex is extremely air and moisture sensitive, whereas ferrocene complex is highly inert. Reason
Yes,
is
sir.
also written in that slide. So these types of question can be asked with that, like, statement question. So I identify the correct statement. Okay.
Yes, sir.
So let's say in the fourth statement they will say that ferrocene is highly stable, beryllium is highly stable, this one is stable, this one is unstable, and they add later on the reason for the stability. Now what is the reason for the stability for the ferrocene?
The electronegativity has been taken, sir.
Yes, so electronegativity, you can see for the iron electronegativity is only 1.6, and for the beryllium it is 1.8. For the
Say
beryllium it
1.8.
is 1.6, and here
Yes,
both
sir.
side the carbon is there, that is the cyclopentadienyl. So carbon,
Yes,
if you
sir.
consider the ligand, if you consider the two ligand, that is the both are cyclopentadienyl, and they will not that much have different in the electronegativity. When you are
Yes, sir.
considering the metal center, that is beryllium and iron, 1.6 and 1.8, there is also not very much differential electronegativity, 1.6 and 1.8. So what is the difference between these two complex? That beryllium is an X block element, okay, whereas iron is a D block element. So metal ligand interaction is highly strong for the iron, because of the d orbitals available for the iron, it can form a covalent bonding with the
The coordinate covalent bond.
uh, covalent bonding with the CP ring, whereas for the beryllium d orbitals are unavailable and it cannot form the, you say, covalent bond. So these complex become ionic in nature. So that's why
Yes.
the covalent compound gives the maximum stability than the ionic compound. Here, as the ionic bond is formed between the beryllium and the CPD, that's why it is highly unstable.
Okay, sir.
So, and that structure you are saying, let me see where it is. That bridging CO and terminal CO I am discussing. So next day I will try to. Another important question is that metal carbon multiple bond. So three types of bond is there when you are considering the polarity for metal carbon bond. So one can be the metal carbon sigma bond, metal carbon pi bond, another is metal carbon delta bond. So
Yes, sir.
but the formation of these three bond is not independent. So the pi bond and the delta bond will be always formed after subsequent formation of sigma bond.
Yes, sir.
Okay, so without the sigma bond, pi
Yes, sir.
bond cannot be formed, and without the pi bond, delta bond cannot be formed.
Okay, form.
So this is the metals. Okay.
Yes, sir. Okay, sir.
Here, this page. So here you can see in this example that chromium CO5 Cr double bond Cr2, where this one is chromium and there is an alkyl group attached to the carbon. So this is a metal carbon multiple bonded compound, and here so here two bond is there. So for the two bond, one bond should be sigma bond, another one would be pi bond. So here, so the pi sigma bond, we know that sigma bond don't have any nodal plane. Okay, sigma bond will be formed with the head-on overlap, so there will be no possibility of forming nodal plane. When we are talking about the pi bond can form in two ways, one with the head-on overlap, another with the side-on overlap. So there is a formation of nodal plane. So pi bond has one nodal plane. But for this compound, the second one, RE4, a R4, RE, so four bonds, rhenium and R4. So here you can see all the three types of bonding is there. So first it will form the sigma bond, following by subsequent two pi bonds, and then the fourth one will be the delta bond. So okay, so delta bond have two nodes, two nodal plane. So this can also be asked that pi bond has one nodal plane, whereas the delta bond have two nodal plane. Then you have to draw this in your any other exam, draw this picture and have to explain why the delta bond have two nodal plane, right? And delta bond is formed. So here we know that in the d orbital we have three different kinds of orbital, that is the d, T2g and Eg. For the
EG.
T2g and Eg, whereas the Eg orbital, that is the dz square and dx square minus
E x square
y
minus y square, E z
square.
square.
So these Eg orbital involves in sigma bonding formation, right?
Yes, sir.
Because their orientation along the axis, because dz square and dz x square minus y square orbital orient along the axis, whereas
Along the axis.
the T2g orbital have three orbital. What are they?
dxy, dyz, dxz.
So there is three orbital.
Yes, sir.
In these three orbital, which orbitals participate in pi bond formation?
Pi bond formation. This is dyz and dxz.
Yes. So dxz and dyz involved in the pi bond formation, and rest
Yes.
remaining dxy. This will be involved formation of a delta
Delta bond.
Okay. So
Yes,
Eg
sir.
orbital, that is the g z square and d x square minus y square, will involve in the sigma bond formation. P xz and p yz orbital will be formation of the pi bond, and d xy orbital will be involving in the formation of delta bond. What is the condition? Everything will be changed if you change the axis. So when we are saying this, we have to say that z axis is the internuclear axis. So we are considering that the sigma bond formation occurs along the z axis. Okay. If you say that sigma bond formation occur along the x axis or y axis, then all the configuration will be different. So convention is the sigma bond formation, when you form the sigma bond, it should be along the z axis. Only in that case we can determine that xz and yz, dxz yz from the pi orbital, whereas gxy from the delta orbital. Is clear the orbital picture? Next day I will discuss in detail this orbital interaction.
Sir, one more thing. Delta bond is formed by dxy and dxy minus y square as well.
No, both are same, dxy and dxy.
Okay, sir. But sir, dz square forms sigma bond, right?
dz square from sigma bond and dx square minus y square, the orbital which lobes are along the axis, that are
Yes, sir.
involving. You have to just know the structure of
Yes,
this.
sir. Yes, sir.
This pen. So here, if you say dx square minus y square, that lobes are along the axis, so that will cannot form the pi bond. So sigma bond
Yes, sir, that
will be formed along the axis. So these two orbital dxy and dx square minus y square and dz square, these two orbital lobes aligned along the axis. So that's why these two will be involving in the sigma bond formation, and that energy will be lowered. That's why we have Eg star orbital, where the extra electron coming. We will also discuss in the first question. Okay. So next day I will show it.
Okay, sir.
Another thing came is the group electronegativity. It is also very important thing when you are considering the different substituent on the carbon atom. So when you are considering the metal carbon bond, group electronegativity play an very important role. How? Let's say we have two molecules. One is CH3 attached to the metal, another is CF3, that is trifluorocarbon, CF trifluoromethane, CF3 attached to the metal. So for that case, which bond, if the metal is same or other configuration is same, let's say which metal carbon bond will be more polar?
So is it metal bonded to CF3?
Yes, because fluorine has a high
Electron
electronegativity.
withdrawing nature. Yeah.
Because electron withdrawing nature. Fluorine has a high electronegativity than higher electronegativity than H. So that
Hydrogen.
electron withdrawing effect for the fluorine will be more, and that why the the extent of charge separation, that is the negative charge separation on the carbon, will be more compared to the CH3. That's why this bond will be more stretchable, and that bond will be more polar bond. And more
Yes.
polar bond means the bond is more weaker.
We
Polarity
can.
changes and it decreasing the bond strength.
Yes, sir.
And polarity depends on the electronegativity of the substituent. Now, if the substituent this we discuss the substituent on the carbon atom. Now, if the substituent is present on the metal center, that also depends the thing. Let's say here you can see that C ethyl group is there in that slide,
Yes, sir.
and here
Yes,
C
sir.
chlorides group
Immediately
is
three.
there. So, so
Yes,
ethyl
sir.
group is the electron donating group, whereas
Yes,
the
sir.
chloride group is an electron withdrawing group.
Withdrawing group.
So
Yes,
group
sir.
electronegativity is reversal of the polarity. So because of the highly electron donating nature of the ethylene, the germanium center become highly positively negatively charged. Because of that, ethyl
Yes.
is donating electrons to the germanium, whereas the chloride, which becomes the electron negativity, electron withdrawing, so it will withdraw the electron from the germanium, so germanium center will be positively charged. So here you can
Yes,
see
sir.
that by changing on the substituent on the center, we can just change the polarity. This is called the reversal of the polarity. So multiple group when attached to the metal, it can change the polarity of the metal center. Okay.
Yes, sir.
Another thing. So when for that like F block elements, so they consider the electronegativity range is not changes so much. That's why whatever the substituent on the metal center for the F block, that decide the polarity of the metal center. So this hopefully discussed the beryllium and kerosene. After that, what do we have? This is also that metal carbon bond is always shorter and stronger interaction. So if the bond is strong, then if the interaction is strong, then bond will be shorter. If the interaction is weaker, then the bond will be longer. Okay, so metal carbon bond is always also the weaker bond compared to that the nitrogen bond, oxygen bond, or halide, because you can also say that electronegativity is higher compared to this, so their bond formation will be more stronger.
Yes, sir.
So we have completed up to lecture 3, so that's why I am not going to start discuss the lecture 4 and 5. So lecture 4 and 5, let me briefly discuss, so when you read, you will get an idea. So lecture 4 and 5 is that how we can consider or how we can determine or see explain a general idea about the bond dissociation energy. So here the bond dissociation energy means the dissociation energy, the energy which is required to break the metal carbon bond only. The bond dissociation energy, when we are talking about the metal carbon bond, not the metal with other ligand or other carbon bond. So here it's a few things it depends on, that is the oxidation state of the metal. How oxidation state? That means if the metal is highly oxidation state, so that means there will be difference in polarity and ligand environment. So that means that L which is already attached to the metal other than carbon. So if the nature of the ligand which is electron withdrawing, electron donating, sigma donating, pi accepting, that depend, and the nature of the substituent on the X. As we have already said, when it is hydrogen the polarity is different, when it is fluorine the polarity is different. And the overall steric effect, how overall steric effect, that if the surrounding metal center and the surrounding ligand in the metal center is highly sterically demanding, then also because of the steric region bond strength gets different. And next we'll read it or see the lecture in more detail. I'm just giving an idea what is there in the upcoming lecture 4 and 5. Yes, here you can see that the bond metal carbon bond energy covered in wide range. So here you can see that boron, trimethyl arsenic and bismuth. So from lower down the group, so bond dissociation decreases and ligand has to be, so from lower down the group, so for the same ligand system the bond dissociation energy decreases.
Okay, sir.
1 minute. And the last video, that is the lecture 5, we will have that concept of 18 electrons. So this is just the lecture 4 and 5 which we have already discussed. So here you can see how this 18 electron is coming. So 5 orbital from the D, 1 orbital from the S and 3 orbitals, so that is giving the 9 orbital totals, which will give the 18 valence electron. And if all the orbitals are filled, then these all our orbitals are for the bonding orbitals. That's why we stopped at 18. When we have the extra electron, we have to put that extra electron in the anti-bonding orbital. That's why after that the compound getting unstable. And another question is that the 22 which I also discussed, that is also there. I also discussed, and there is the MO diagram I will show in in the next series, and we will discuss that hemodiagram to see whether it is here or not. Here you can see the structure of Fe2CO9. You can see it. Can you see?
Yes, sir.
Yeah. So you can see that 3 carbonyl groups are terminal for each of the other, and for another 3 carbonyl is the bridging. But for the manganese is the all carbonyl groups are how terminal. There is no bridging. So this manganese structure, this Fe2CO9 structure, and another structure will come, that is Fe3CO12. So these 3-4 structure you have to just remember for this question. So this can be asked, and this here this is the orbital diagram which I am discussing. Okay, here.
Yes.
So here you can see that here we have the d orbital. So d orbital gives the 2 level. So here this is T2G, and here which is remains as a non-bonding orbital, and bonding is the Eg. Okay. So now here is the NS orbital and NP orbital. Now Eg will perform in the bonding orbital. So there will be anti-bonding orbital of Eg star A1G from the S configuration, S orbital. It will also form in the bonding. So it will have the A1G star, and P orbital, that is form in the bonding orbital, that also have the anti-bonding of T1U star, that is you can call it P star. So this is the energy, that is the T2G and Eg star. This separation is called the delta O, and we can fill the electron according to the energy up to this Eg star. So here total 80 electron up to this T2G, and Eg holds another 4 electron. So that's why 22 electron is the maximum number of electron which can be put in the transition metal in a system. So if you put 23 electron, it will go in the A1G star, which is highly unstable, because the energy of this A1G star and T1U star, that is from the S P contribution,
Higher.
will be very higher. So that cannot be occupied, and it cannot stabilize. So this orbital will only give the 22 maximum number of electrons. That's why the 22 number came. It cannot be more than 22. Okay?
Yes, sir. If some more electrons has to be accommodated apart from bonding, like if the bonding atom is full and some more electrons are present, like 4 electrons, it can be accommodated to Eg star, but it can't go beyond T1G and T1U.
And it will not go beyond T1G star. So, up to 18,
Yes, sir.
this level will be filled up to 18. Okay. So
Yes,
after
sir.
that 19, 20, 21 and 22 will be held in this Eg star, and after that 23 will be go to the A1G star. And but because of the higher energy, it is not possible to go to this higher energy available. That's why the energy for the complexes maximum will have maximum number of 22 electrons.
Okay, sir.
Okay. This
Okay, sir.
So this will be see in the lecture 5.
Sir.
Here it is discussed in more detail. Here, so it says that. Okay.
Yes, sir.
So the complexes can see the class 1 complexes, therefore be 12 to 22 valence electron, not more than that.
Yes, sir.
Then we will go to the lecture 6, which I will discuss in the later, how that class 1, class 2 and how this energy level differs. Okay then?
Yes, sir.
Do you have any other
Okay,
questions?
fine. No, sir. That's it.
Okay, so you get this, you can get this PDF. Let's see. You can get this PDF from this study material or books. You click on you will have this page, right?
Yes, sir.
When you open this,
Yes.
in the left side, you go to these books and you can click on the English book. Okay, so when you click on it, it will give you this book which I show you. So it is available on the portal. When you solve the assignment, just click on this and you will get the link to download this book. So you read this book, because multiple time you cannot see the lecture videos, but if you read this book, this is exactly same with the lecture videos. Okay, so
Yes, sir.
after one time seeing the lecture video, just read it, or you can also
Okay, sir.
mark it on the, and you get the slides from in this book also. Okay, so there is no, I don't have to share the
Okay,
slide.
sir.
I will only share the questions which I have discussed. Any doubt regarding that assignment question or anything, you can ask me in the next
No,
session.
sir. I'll go through that book and let you know.
Huh. Okay. Okay then.
Okay, sir.
Okay then. Thank you for joining.
Thank you, sir. Thank you very
See you in
much.
the next Sunday. Okay. Okay then. As we have discussed that 10 questions along with that important topics which has been covered in this week. So I hope this video will be helpful for solving your assignment. And if you have any doubt or any question regarding that weekly content, please express it in the live session. Or if you have any doubt regarding the portal assignment or portal problem, you can directly post it in that uh, discussion forum, or you can also ask me. So we'll see you in the next upcoming Sunday, that will be uh, uh, 3rd of August. So we'll see you. And best way to do this session is to interact, and if you have any doubt, you can just ask me. I will try to explain as rigorously as it can be. Okay, I stop this session here, and you will get that recording sheet list, and you will get that uh, questions and answer from there also. Thank you for joining.